Good morning, everyone. I hope everybody's doing well today. We're getting back into our summertime weather. Nice and warm and lots of rain, but that's good. I've told you all many times about the issues with rain and trying to navigate Mother Nature, especially when you try to fly to the East Coast. Um, for the lecture part on Monday, I made an additional comment when I posted the recording. But before I go into the lecture, I just want to remind you, um, I'll have some information up about the final by the end of the week. Again, like an email announcement, Blackboard announcement, and there's also a practice final up on the practice test for you all to look at and to go ahead and think about. And I'll probably do some review problems Monday next week to kind of encapsulate the entire term. And then, of course, remember you have a signature assignment that's a due at the end of this week, which is basically another quiz grade. And it's a very straightforward problem utilizing the techniques from chapter 7 with uh, volumes of regions of solids of revolution, things like that, where we take the region and we revolve about a particular axis. So that, again, not very difficult, but again, just a critical thinking exercise. And I've said many times, that's what you do in math every day. So you will not find it overly challenging, but it's certainly another uh, uh, example where you can get a straightforward quiz grade. And so I wanted to give you, as I've said before, I wanted to give you a reason to even want to do it. If if an assignment doesn't count anything, then it's really not quite worth the trouble. And I certainly understand that. So what I wanted to do was make one allusion to what I wrote for the lecture recording. Remember, I just on the cuff said, well, let's just go ahead and show we have polar axis symmetry. And I made the comment that if you just substitute the additive inverse of theta for theta, you don't get any change. And that's a simple way. But of course, I wanted to go out on the limb and do this. But I remember from the lecture recording, I had changed this to a negative incorrectly. And so you don't get the same equation, but it's not the equation that we got. And I made the comment that the even though the form is not exactly the beginning one, it would be traversed in the opposite direction, which is technically true. But what I wanted to do was actually write it where I had the correct sign here. And so when you do the arithmetic here, note we think of this like we do in college algebra when we're doing the Cartesian graph. And so what I did is I rewrote this where it's basically a shift downward, a vertical downward shift, like here that you say in college algebra when you don't know much, by 8. And so when you draw it, you see that it's shifted from the one that we had in class. But notice, because all these are negatives, instead of moving in a direction here, we're all shooting through the origin because all these values are negative. So we were not up here when we start, we're down here. And so we actually traverse the exact same curve, but in the opposite direction. So the thing is that with polar coordinates, with the first interchange here, you get the exact equation. Here, you get an equation that gives an equivalent output curve. I remember I said something, it does not change the output curve, but that's the anomaly with polar coordinates. You can still get something that's equivalent even though it doesn't look that way. And so that was what I was basically trying to get across in the lecture. Polar coordinates are very useful, but they are not so simple that you could teach them to an Algebra 2 student or something like that. It requires maturity and a higher level of thinking that students at that level just apparently do not have. So again, when you think about this, if you try this out, this type of technique, don't be concerned if you don't get the exact same equation. Think about it like this and just basically see that you are again generating the same output curve, but the traversal may be reversed as we have in this case. So I thought that was an interesting topic. Lots of times when I teach, of course, I'll say, well, let's just do this and see what happens. Because when you draw curves, you know, it's not a proof. Clearly, this looks like it has polar axis symmetry, but that's not a proof, you know, and of course, if we're doing a problem and we're thinking, oh, okay, we're going to use the symmetry of the Cartesian curve. When you look at this, you're thinking there's got to be some kind of symmetry that we get over here, even though it's not going to look the same. This actually foretells the symmetry here in an intuitive way. Okay, so now what we want to do today is talk about some more calculus. And again, this is some fun stuff. I think in the way that, yeah, let me refocus this a little bit. In that we're basically going to think about areas today, focus on that. And as we do some of the areas, I'm going to do another curve that I didn't have time to do last lecture called the lemniscate. But I just want to let you know or remind you that when it comes to these polar curves, you've got this nice little summary here that gives you very simple circles, the rose curves, the limacons, and then of course we're going to talk about the lemniscate today. So this is a wonderful tool that you can just print from your uh, textbook, your ebook, and just like with the Power Series, it gives you a very quick reference to kind of push all the ideas forward. Now, when it comes to areas of polar curves, what we can do, and I want to do this kind of intuitively, because again, you know, it's sometimes nice to just see a picture. So when we think the only problem with the polar curves, ladies and gentlemen, is that they're not Cartesian. So we can't just thrust everything we think about Cartesian onto the polar curves, even though we find that the Cartesian curve helps us draw the polar curve, you know, so easily. I mean, it's like the points that we need, we get from the Cartesian curve, and we make the transfer, and it makes it almost effortless. You often see instances where people are plotting points with polar curves, and that is not going to help you do anything. It's beside the logic. And so this idea of looking at the Cartesian and going to the polar is very good. So let's, for instance, think that we have a polar curve that's non-negative. So we'll say non-negative for, we'll just say theta, and this is usually the letters that we use. We use an alpha and a beta. And so basically what this means is that the difference is not going to exceed 2 pi. So we'll just say that here's our little restriction. We'll say that we have something like this: beta minus alpha will not exceed 2 pi. So we can think, and then of course, we're going to say, well, if we've got a polar curve, you know, in Cartesian, we have like vertical lines or horizontal lines and things like that. So now instead of that, we're going to think about the axial lines. So for instance, say we have a polar curve that looks something like this, and we have some axial lines. So we're going to think of, say, something like this. We'll have theta equal, in this case, we'll take this to be the upper beta, and say we have theta equals alpha. Okay, and so here's our polar curve. I'm not going to call this r equal f of theta. I've already told you about, I don't like all the extra letters. letters are useless when they just get in the way. And I minimize notation, as you well know, as you should do. And I appreciate the fact that you all are bringing up the level of your computation. It's a very, very big difference grading a pre-calculus test and a calculus 2 test. I know there's a lot of growth that occurs between those classes, and I'm glad to see the growth in your work. So the idea is that if you were thinking about a polar area, you would be considering this shaded area here. And so what we want to do is think of just chopping this up so that we basically imitate the sector of a circle when we think infinitesimally. So the idea here is to partition. I said I was going to keep this intuitive, but you still have to say this. We want a partition of alpha beta. So we could say alpha equals theta 0, theta 1, and then we can go theta I minus 1, theta I for the ith subinterval. And then we'll extend to theta n, which is beta. So this is our ith subinterval, just like in calculus 1. And so we can think of that so theta sub I minus 1. Well, that's theta equals that and theta equals that, but of course I run out of letters, so we'll just leave it like that. And then we look at this. And we approximate this area using the sector area of a circle. Okay, so just like in calculus 1, if we did the standard Riemann integration for each subinterval, we would approximate the area by a rectangle. And so, of course, depending on whether the function were increasing or decreasing, we get an inscribed rectangle or a circumscribed rectangle. So you could think about just kind of thinking of a curve of a circle running across here. So it's the same setup. It's just that when you do this, it appeals to your knowledge of the geometry of a circle. So this would imply, we'll just say area bounded by r theta and the axial lines theta equal alpha and theta equal beta is. Okay, so we'll think of it as a limit of a Riemann sum. So we'll say the limit as the norm of the partition tends to 0. So we're back to Cal 1, which you probably prefer anyway. So we have our sum I equals 1 to n from our partition. And then we've got 1/2 r squared. So now what you do, you think, well, we just usually want to use an element in the ith subinterval. So here, let me clean this up a little bit. We'll just do this. I'll just say take c sub I in the ith subinterval. So we in the Riemann sum, we can evaluate anywhere in the ith subinterval. So we'll say r of c sub I quantity squared, and then of course delta theta sub I, which is just the difference between where did I write it? Right there, theta sub I minus theta sub I minus 1, which we just write that way. So now this basically sums all of the sector areas. And when we actually do this, when we let the norm go to 0, and of course, we're assuming that theta, not only is it non-negative, but it's continuous, so we can integrate it. So that would be a good thing too. We have fairly nice curves, so we can know that the Riemann integral exists of this. So this will give us 1/2. Of course, the partition runs from alpha to beta, so that gives us the limits. And then we'll just have r squared of theta d theta. Now, when you look at this, you're thinking how simple and true, but again, it's kind of looks like the arc length formula. You've got a square, but no radical. So the key here is that when you think about polar areas where you're just given a polar curve and a set of axial lines, it's just like, okay, let's do some sector areas. So this is where you start seeing the use of what you did in pre-cal. And maybe you wonder why we even cared about, arc length, and we even cared about sector areas and things like this. Sometimes the arguments that we're doing now gets kicked out of Cal 2, and then it's like extra reading before the students take Calculus 3. But at San Jac, we try to make sure that you get this so you're prepared for Calculus 3. So now, if we look at this, we're thinking, okay, well, let's just try this out. So now what we're going to do is we're going to look at our polar curves and maybe try to compute areas that are contained within a loop of a polar curve. And then maybe we want to try to intersect curves and figure out areas that are common to both. The idea is that we have to think polar now, but at least we have some structure to do that. And this will be the recipe that we will apply. Even though it's very simple, we're going to find that the setup will require that we really think about this new coordinate system, polar coordinates. Polar coordinates are indispensable, and you will use them here and forevermore in STEM. So let's look at some examples of the use of this. I thought I'd start out with a real simple curve, basically a circle. So here's a simple example. So we want to compute area, basically compute area. And in this case, this would be the interior of r equals 6 sine theta. Now, of course, you really wouldn't need the calculus to do this, but I want to use this as a nice introductory example. So how will we do this? Okay, just think back to what we did in chapter 7, where because we, are creatures of pictures, we sketch the curves, we figure out what the region looks like, and then we analyze the region algebraically, and then transfer that algebra to the integral. Well, here's the same thing. So there is no difference in the technique. So don't look at this like something difficult. I know a lot of you are very quick to move forward. I mean, I know some of you even do homework during lecture, which is good. I kind of laugh at that because I look at your login information and you're doing your homework while I'm lecturing, and that is very efficient. So good for you, but somewhat amusing. So now what we want to do is think of this as a Cartesian curve and then draw the corresponding polar curve. So this is easy. This is like, what is it? Let me make sure this light is on. Yeah, it's on. You can see that's when I turned the IPEVO light off, and that's when I turned the IPEVO light on. And sometimes it doesn't always appear to me that it's on, but it is. I guess it's just a little bit more dreary this morning. So now we can draw this easily. I mean, this is like one of the curves that you just do in your head, but the simplicity doing this makes drawing the polar curve so easy. So of course, this is just what we'll just think of a 6 and a -6. And we're not going to need, to draw the whole thing to get the entire curve, but let's just go ahead and do one complete period, which would be 2 pi. And so we'll break that up into 4 pieces. So pi over 2 pi, 3 pi over 2, and 2 pi. So we'll just, same song and dance, but like I say, the little effort here is rewarded handsomely. So what we're seeing in this particular case, and we don't always know, we notice that like I said before, if we're doing rose curves, it usually takes a little bit more curve to get all the petals out, but it just every curve is different, and so the analysis is not immediate. But what we can see here is that this is a very simple curve. This is actually going to define a circle in the polar plane. So we can kind of dot in or do it like that if you like, and then the polar axis. So at this point, we can just kind of relax and say, now this is the polar plane, the theta equals 0, theta equal pi over 2, positive or polar axis here. So now notice we start out at 0, but we end up here at 6. Here's a 3, and here's a 6. If you've looked in the Blackboard notes, this is just a circle. This is just a Cartesian circle. So now notice as we loop up to pi over 2, and these are all positive here, we end up on the theta equal pi over 2 axis, but we've grown from 0 radius. Well, here we'll just start drawing 0 radius to 6. And now we do the same, but we end up at pi where we are back at the pole, but we're still positive, so there's no translation going on. So we just get a circle, even though this is not Rembrandt. Again, if you look at this and you do the translation uh, in Cartesian, you basically just get a circle whose center is on the y-axis. Basically, the center is at a over 2, 0 a over 2, which is in this case 3, and it turns out to also be the radius. So do that calculation when you have time, but when if we had 6 cosine theta, the circle would be right here, opening like that along the polar axis. So these are real simple circles in polar coordinates. Here's the Cartesian graph, here's the polar graph. Again, very different, but drawing this helps us draw this with, and then of course, if you recognize this as one of our standard circles right here, you see the circle right here, the Cartesian or polar curve that we wrote from the Cartesian graph, it's organized here, and then the one for cosine organized here. So if you already notice that form, when you do this, you're like, oh, that's a circle, and you can quickly draw it. So now when you think of this, you think of this axial, let's think of it this way. We've got theta equals 0, which is the whole thing. And then of course we could describe it as theta here equals pi. So this could be our alpha, and this could be our beta. And then, of course, here's our non-negative curve. So as you move through here, the radius starts here, and then it moves out to here, and it moves, you can just draw some radii if you want, things like that, as we move around the circle. And so we can think of computing the area of this, which we know how to do, but let's just go ahead and use the formula just to get some practice with it. So if we looked at this, this curve is ready to go. We have the algebra involving the alpha and the beta. So we could say this implies that the area that we need, we'll just call it A for now. We might be a little bit more descriptive when the problem's more complicated. So we'll have 1/2, again, 0 to pi. So again, here we'll take alpha beta to be 0 to pi. And then, of course, we square. So we have 6 sine theta, quantity squared, d theta. And that was the definition that we came up with. So now this will give us 1/2. And then, of course, when we square, we get a 36. 0 to pi of sine squared theta d theta. Our friend from our trig integrals, right? So we've got what, 18 there. And now we can analyze this just using the power reducing. So we have the 1/2. So I'll go ahead and move the 1/2 outside, and that will be 1 minus cosine 2 theta using the power reducing. Our good friend, Pythagorean identities, that we live for them. We have to have them. So now this gives us 9, and we can integrate. So of course we'll get a theta, and the antiderivative of cosine is the positive sign. So this gives us minus 1/2 sine 2 theta, 0 to pi. So this will give us 9. So we have what? We have a theta, which is replaced by pi, minus 1/2 sine 2 pi. And then, of course, if we put in 0, I mean, we don't even have to write that down. That's a 0 minus a 0. We clearly know sine of 0 is 0. And now, of course, the sine of 2 pi, again, that's on the x-axis. That, again, is 0. So we just get 9 times pi minus 0, which is 9 pi, which is clearly what you get if you use the formula pi r squared. So the point here was just to do a very straightforward example of the application of this formula so that you can see that when we do all of this, you're thinking, well, all of this is tied up together. We assume circles to get this formula. So it's really not the best mathematics to do it. We just say, well, pi r squared, and we're done. But I thought this would just be a very simple way to show you how the formula works. Because again, when we use certain constructs to prove others, we don't kind of reprove them, and run in circles. But what's nice about this is that we can actually have a very simple application of the formula. And hopefully it makes sense to you. Now, what I want to do is look at a curve that we did not cover the last time. Now, of course, if you're doing a rose curve, the question might ask, well, find the area enclosed by a single petal or 2 petals or whatever. And so you just do your Cartesian, and you can basically find your limits from the Cartesian graph. But again, the Cartesian will give you plenty of information when you do these. So don't be afraid of them. And just remember that when you got the cosine, the petal starts on the polar axis. When it's sine, you start at 0. So the first petal is offset from the polar axis. So I'll say something about that eventually. So here, let's look at this example. We want the interior, and this gives us a good application that I didn't cover last class. Interior of the lemniscate, r squared equals 6 sine 2 theta. This is called a lemniscate. It's a figure 8 lemniscate. And When we say interior, there are going to be two loops. So by the symmetry of the curve, we can just, for instance, compute the area enclosed by one and double it. So that is something we're accustomed to. Now, when you look at this, you're thinking this doesn't make sense because this curve can be negative. The output here could clearly be negative. That's what you learn in trigonometry. I mean, this is a sine function, right? So this is implicit. And so it doesn't really make sense, but this is the way the curve is always listed. So you're thinking if you took principal square roots, you'd get a positive square root. And then of course, by the square root property, you'd have a negative. So, and that's not going to change anything. That's going to be like, basically looking at a curve that's traversed differently. But the idea here is that whichever curve we choose, the positive square root or the negative, the curves will be traced so that the curves are symmetric. That is, the areas won't change. So what is customary here is to look at the principal square root and then use the Cartesian graph to draw it. So here's what we'll do. We will analyze. This is where I remember as a kid, I thought this Cartesian strategy is important. So we're going to analyze the principal square root. So that'll give us a square root of 6. And then we'll have sine 2 theta 1/2. Now, when you think about this and you think about what we're doing, you'll say, okay, well, what could we do? We could just go ahead and look at the graph of this roughly, and then pick off where it's non-negative, right? And then draw the graph just for the non-negative part. So that's the trick that we're using. So at this point, you can also even think about this way, because this part will give us the actual radius here. And we can go ahead and put that in our graph, but then we're just going to be looking at this when I draw it. So it's kind of an amalgamation graph, not exactly. So in this point, what we'll say is we will graph in the Cartesian sense. Cartesian, we'll just look at square root 6 sine 2 theta. And then we'll ignore, and then of course, since the maximum, is 1 when we square root it, we don't get a completely different curve. It's not going to look exactly the same, but the maximum value will not be altered. So the idea here is that this will be okay when we do our analysis. This is a standard trick, and it works. So now, of course, what we can do is we'll just do square root 6, negative square root 6. So we're just going to look at this guy without the square root on the sign. And then what we can do, and I always, sorry, let me just move this down a little bit. I tend to put the first one too high. So it's about right here. So that looks better. So now, of course, the period's going to be cut in half to pi. So we can just basically do what? Pi over 4. So pi over 4, pi halves, 3 pi over 4, pi. Pi over 4. So we've just got period is 2 pi divided by 2, which is pi. So now when we think about this, we have a 0, we have the 2, 0, the negative, like that. And we can do some extra too. I should just write these all in terms of fours, but these are so easy. We know how to do them. They're just simple. I'm just doing an extra period here. So this is like a graphing exercise first and foremost, and then we're going to put it into an area exercise like this. So when you look at this and you think about this, this part gets a check, but of course we can't, in the real plane, none of this would make any sense. So these would be values of this curve here, this function here, that would not have real outputs, okay? So we ignore this. So this is gonna give us one loop here. So this is one loop. So if you wanna just kind of color it in, this is one loop, and here's another one. But then as we keep going, we're not going to see much difference here because basically we're going to have the same setup here. So these two loops here, we can think of them as loops in a Cartesian, will give us the two loops of the figure 8. So again, these we just ignore. I mean, ignore because this is less than 0. We ignore. No real output here. Ignore. I don't want you to look at this technique and be baffled by it. I want you to understand it because it is the only way to draw these and have any at all confidence that the graph is correct. So the technique is excellent. So now we'll just, we'll be a little bit, okay, we'll just go ahead and draw the polar axis and not worry about so many dotted lines. And then theta equal pi over 2. And now, of course, we've got some nice geometry here. We've got a pi over 4. So we'll just go ahead and use our square to get that line. You can always guesstimate just thinking about the unit circle. And then, of course, we could get the 5 pi over 4. But that's there, but let me go ahead and draw this. So in this case, so what I wanted to do was just go ahead and draw this. Notice we don't really need this, but it kind of gives you some perspective because that one's just going to be right there, obviously. But I'm just giving you some perspective as to, what's going on in the plane. So now when we look at this, we're thinking we start out at the pole and then we grow to pi over 4 and then we diminish right back to create a loop. So let's draw it. And of course, we'll go out to the maximum square root 6 for R. Like that. Now, of course, this is not Rembrandt. And one of my private pre-cal students, I feel like private students because they come to office hours all the time. And I said, well, you're going to learn this pre-cal really well. He says, well, if I do something on the test that doesn't look beautiful, I'll say it's not Rembrandt. I said, yeah, touche. So now when you do this, you get this loop, but then after this, it stops. But then as you get to this point, you're starting again, but you're moving out at pi. So there's kind of a kink here. It's not going to travel this way. There's a real pathology going on here. It's going to move this way. So it's the little kink and then it runs this way. So this kind of starts out like this. And then you do the same here. We can just kind of have a little point there. Like that. So this moves this way. So there's your figure 8. Now, the thing is that it takes these two to get it. And after that, you just keep retracing. And of course, if you did the negative, this would be flipped. and then you would be over here. So basically, if you want, you can just go ahead and dot this in if we did the negative. But then when you think of 3 pi over 4, you're thinking of moving up to there, but you're shooting through here. So you're going to get a figure 8 that's running here, but it'll have the same areas. So we're just picking on the positive here. Okay, so this is implicit equations, just like we do in Cartesian, but we're thinking polar. So the arithmetic is not that difficult as long as you keep in mind how we've defined polar coordinates. Because we have to know that in this case, R is directed distance. So it can take on negative values. And that's like crazy. A distance is negative. That makes no sense. I mean, you wonder why you have pre-calc students that don't have any problem with writing a negative value for the length of the side of a triangle. And I'm thinking, what are you doing? But I'm like, okay, if it gets you to the finish line, it's all right. But I said, don't be surprised if there's some issues down the road. Now I'm telling you it's okay. So it's a very different way of looking at things. So now when you look at this, so look at this, ladies and gentlemen, as just an exercise in doing the figure 8. And then when you see that, these are the curves that you see right here. Okay. So this chart is very useful. So now it says interior of the figure 8. So basically, we'll just do the first quadrant area and we'll multiply by 2. So now notice we have a very simple setup here. If you look at this, we've got the alpha here will just be what? 0, and the beta will just be what? Pi over 2. And we've got a nice non-negative curve, no issues, so we're good to go. So here we'll take alpha equals 0, beta equal pi over 2, and we'll double the result. When it's easy to double the result in one computation, we'll do that. Otherwise, we may just hold off on it and then multiply at the end just to declutter the computation. So now we'll say area of interior. And this is not a hard calculation. Some of the calculations will get harder than others. There's one that will take us a little bit more time. So for instance, we'll have 2 times, again, we've got the 1/2, 0 to pi over 2. And now notice we've got, and this is where you look and say, okay, well, how do we proceed with this? The thing is that this is our curve and there's the square right there. So don't square the square. So here's what we're looking at. And then when we square it, we get exactly that. So this is 6 sine 2 theta. So just remember, this is r squared, because we have to start with an implicit equation. So remember that when you do this. So this will give us, now if we look at this, this absorbs and we can factor the 6. So we get a real easy integral. So we'll just, the antiderivative of the sine is the negative cosine. So we'll get 6 and we'll get a negative 1/2 cosine 2 theta 0 pi over 2. So this gives us a negative 3. So we'll have cosine. Again, we have 2 times pi over 2. That'll be cosine of pi. And then cosine of 0. So this will be a negative 3. And then, of course, cosine of pi is negative 1. Cosine of 0 is 1 minus 1. So this gives us a -3 times a -2, which is a 6. So sometimes you get some answers with these problems that mystify you, because remember when we did this with the Cartesian, we always got these really, everything had a pi in it. We'd have these strange numbers and all. Rarely did we get nice looking numbers like this. So that's kind of a surprise with some of these polar areas that you don't expect at all. But again, the calculus is very interesting how it evolves through different types of structure, especially with the polar coordinates. And I think that the great mathematicians enjoyed the polar coordinates. They really did. I think we understand them better now because we have a better notation. Now let's look at another example before we move to arc length. There are tons of examples. I mean, calculus, you can do calculus for years and never feel like you've covered everything. It's like doing number theory. There's plenty to be done. Now, what I wanted to do is give you an example of a area calculation. But before I do this, let's see. I wanna talk about a intersecting setup. This particular one, I'll come back and summarize when I have time. I want to talk about some intersecting curves. For instance, um, in this example, we want to compute, in this case, area of the common interior And when I say that, when we say common interior, we're thinking, okay, well, what is the area that's common to both? So we're thinking about intersection. Now with intersecting curves, we do like we did before, but there might be points of intersection that have different values of theta. I like the way the uh, author tries to make that distinction. And if you look at some of the videos in the textbook, they cover this. But it could be that two curves actually intersect at the same point for differing values of theta, and you'll see that in your homework. So usually when you make your sketch, you'll say, oh, well, these both intersect at the pole, but not at the same value of theta. So, I mean, the intersection point is clearly 0, 0, but it's just really weird when you think about the fact that can occur through differing values of theta, because polar coordinates are not unique. Okay, Cartesian coordinates are. So because you don't have that uniqueness with polar coordinates, you can get these types of anomalies occurring. So here's an excellent example. R equals 4 sine 2 theta, that's a rose curve, and r equals 2, which is just a plain old circle centered at the origin. So again, this is the rose curve that we talked about last time. So what we're going to do is we're going to always look for symmetry. This is going to have 4 petals, and so we can look at the area common in one quadrant, and by virtue of the symmetry, we can basically take that computation and multiply it by 4 to cover the other 3 quadrants. So again, the symmetry is something we've used before, but we will definitely use here to cut down on the amount of calculation. So first, what I want to do is let's just go ahead and get a picture of the rose curve. So notice again, the period is going to be pi, just like we had before, 2 pi over 2, which is pi. And so let's just get a nice picture of this. Again, when you do these problems, is it important to get a fairly good sketch? I will say yes, because the Cartesian graph kind of sets you up for that. Now, of course, you can shortchange this and say, oh, well, we did this in lecture. I don't have to work back through this or whatever. That's fine, but it's nice to have some level of confidence. And then, of course, we'll have what? We'll have the pi over 4, pi over 2. Let's see here. Oh, and then, yeah, we'll do one of these. We'll just do the one loop and then we'll cheat for the rest. So here we've got the 0, 1, 0, negative, or 4, negative 4, 0. So this will get us started. It doesn't generate the whole thing, but it gets us started. So let's look at the polar. So now, when we look at this, we're thinking, okay, so what we'll do like I did before, do our nice little quadrants. Is to get our axial lines. Obviously, the sketches help us to organize the algebra and the analytic geometry, which is basically the same thing, so that we have some confidence in what we're doing. Now, what we can see here is that if you want, we can just say we can mark this off as the 4 and just kind of run around that way. And note that here, this particular loop will give us the curve here. And then, of course, this will be, instead of being here, we're going to end up here, project, instead of at 3/4 or 3 pi over 4, we project through the origin because r is negative, and we get this loop. And then, of course, we can generate the others. So let's go ahead and draw it. I could have come out a little bit farther here. There we go. So there's our rose curve. Again, not Rembrandt, but the idea now is that by the symmetry, and of course, if I continue this on another period, you would get the other pieces, but you see how this works. So we're moving this way, then we grab this one, then we grab that one, then we grab this one, and we're back there. So this is a nice curve, not like the lemniscate that has all the issues at the pole. So again, that we see this is hugely important because it gives us the nice R's here that goes to here very simply. So now if you want, what I want to do is just mark in a circle R equal 2. So again, this is going to, not go all the way to 4 clearly. So I'll just kind of mark this off. See if I can go ahead and draw the circle. So let's see here. There we go. So there's our circle. So the thing is, we've got the area common to both would be this bit. Now I'm going to shade it over here. I don't want to shade here because that's where I'm going to analyze a little bit. So here would be a common area in the second quadrant right here, right there. So this is where this analysis is essential. I just kind of throw it out like, oh, it's obvious. That's the kind of area that we need. That's what we need here, here. So this is in the second quadrant, first, third, and fourth. Okay, so this sketch does help us. So now when we think about this in terms of polar, this is exactly why we did the little analysis at the beginning of lecture. We can see that there are two lunar parts on the edge, and then right in the middle is just a simple sector of a circle. And we're thinking that's how we have to analyze this. So now we can do it. And we will figure out these radial lines here. So we've got this lunar part right here. I'm gonna draw it in blue. Same here by symmetry. So these are lunar parts where we've got an axial line here, 0, and then we have an axial line here. We have an axial line here, and then the axial line here is pi over 2, okay? And now in the middle, we just have the sector, and like, oh, hallelujah, how simple. So here's just a sector of a circle in the middle. This is an elegant problem. I looked through your book and I thought I need to find something else different from what I put in the Blackboard notes. And here's a nice example. So this is just the sector of a circle here in the middle. So this is what I was talking about that's different about the polar coordinates. You can't look at this in terms of Cartesian like we have over here. This helps us draw this. And now we're thinking, okay, if we can do the blue plus the red and then figure that out and then hit it with a 4, we're done. So the beauty of the polar coordinate formula is that it's simple, but we have to think in terms of polar areas here, which is very different. Okay, so you've got to think about the line moving through the region, these axial lines moving through, and how do they cut off particular areas, okay, regions that are within the common area so that we can actually analyze them. Okay, so that's essential. This is a very good technique. And I've used it in the Blackboard notes, but I think here it's just really interesting because there's so much symmetry going on. Usually I like to interlock two circles and show how you do the analysis that way, but this is a little bit different. So now we can say, okay, well, when we look at this and we think, okay, how can I get that point right there? And maybe that point right there. I need to look at the intersection of these two. So that's the analysis we want to do now. So intersection. So let's set these equal. So we have 4 sine 2 theta equals 2. And of course, these don't intersect at the pole, so we don't have to worry about crazy algebra ensuing. So now, of course, if you like, we can factor this. So this will be 4 sine 2 theta minus 2 equals 0. So this gives us 4 sine 2 theta minus 1/2 equals 0. So of course, the divide through by the 4, we don't care about that, but that just basically says if and only if sine 2 theta equals 1/2. And so now what we want to do is just solve this in the that we can here with the multiple angle bit and then move it forward. So now what we can see is we've got what? 2 theta, and this will be in the first quadrant because this is positive. So we have 2 theta equals inverse sine of 1/2. Now, if we're looking for all solutions in this particular case, it's better to think of it this way. So what I've written here is I'll just say, do this and go ahead and extend by the multiple of the period. And then when we divide, we correct the period to pi. Okay, so this is how I teach my pre-cal kids. Go ahead and write this out this way and then divide, otherwise you've got to tack on this last. But if you do this, the division takes care of the period calculation. So now we've got theta, and of course the inverse sine of 1/2 is pi over 6. Plus pi k. So this will give us, in this case, pi over 12 plus, and here we can just write this as 12 pi k over 12. Now, if you look at this, and you think about what we have here, we also have another solution with Professor Ron's lemma, and this would look like this. That is also, and we have what? 2 theta. And this one we just subtract from pi, because this is in the upper arc. So this will be pi minus pi over 6, right up here, plus 2 pi k. So we have theta equals 5 pi over 6 divided by 2 plus 2, well, now get rid of the 2. So this gives us theta equals 5 pi over 12 plus 12 pi over 12 times a k. Now, here's the interesting thing. This will give us all the values in all the other quadrants, but the ones that we're interested in, this is Professor Ron's lemma here. This is what you learn in pre-cal, because if you have a solution to a standard sine equation in the first quadrant, you necessarily have one in the second quadrant, and you get that by subtraction from pi. So that's just pre-cal. But what we're seeing is we got this guy right here, which is that dude right there. Again, this is less than pi over 2. And this guy right here, which is this guy right here. So now we can go up here, and then of course we can use symmetry because we're lazy. So we have theta equals pi over 12, and theta equals 5 pi over 12. Okay, so the key here with this problem is the analysis, can be a little bit more difficult, but it's certainly doable, just a lot of pre-calculus. So now what does this imply? So now we'll just say common area, we'll keep it simple. Common area in quadrant 1 will be, well, we've got what? 1/2, 0 to pi over 12. And now we've got our curve here. So we've got, in this particular case, because we're just cutting it off there. So we've got what? 4 sine 2 theta squared d theta plus, then we have 1/2. And now we're going to go pi over 12 to 5 pi over 12. Pi over 12 to 5 pi over 12. And we just have 2 squared d theta. That's the easy part. That's just the area of the circular sector. This part is just r equal 2. Then plus 1/2 5 pi over 12 pi over 2, 4 sine 2 theta quantity squared d theta. Now, when you think about this and you look at what we've done here, we clearly have symmetry here. So there's no need to do this calculation on the outsides twice. So we'll just say these, you know, will in this case combine by symmetry. And you don't necessarily have to prove that. You can just basically see that there is nothing to keep us from assuming the symmetry here. That is certainly mathematically justified. If this curve were more extravagant, then we would say, oh, that's not a nice, beautiful petal. Well, but these are nice, beautiful sine curves that make beautiful rose curves. And so we can make that assumption. So now what we want to do is just take twice of this. So let me move to the next page. So, and then I'll move this, but I'll get this written down here. So this will equal, in this case, we'll just take twice of this. So we'll have 2 times 1/2 0 pi over 12. And we'll go ahead and square it out. 16 sine squared 2 theta d theta plus 1/2 pi over 12 to 5 pi over 12 for d theta. So when you look at it this way, we're just simplifying this calculation. So we started with this, we did our pre-cal. So this is really pre-cal here. Here's where the calculus sets in. So let's complete it. Okay, so now this will give us a 1. So we have a 16, 0, pi over 12, and we can use the power reducing. So we'll have our 1/2. I'll leave it in for this time for, I don't know why, just make it simpler. So we have 1 minus cosine 4 theta, cosine of the quadruple angle, d theta. And now we have what? Plus 1/2 times 4, and we just have a theta, pi over 12, 5 pi over 12. So good old Professor Ron's lemma from pre-cal. That's not even written up in textbooks. I had to prove my own version of it because in the textbook they say, oh, just draw a picture. Well, how are you going to draw a picture when you have arcsine of 2/3? You know, students have to have something algebraic. So I'm not really understanding that, but it's all good. We do what we have to do. So now we've got what? We've got the 1/2. So this is going to be an 8. So now when we anti-differentiate, we get a theta. And of course, the antiderivative cosine is the positive sign. So we get minus 1/4 sine 4 theta 0 pi over 12 plus 2. And now we have 5 pi over 12 minus pi over 12. So now we have 8. And so we'll just go ahead and substitute. So we have pi over 12 minus, so we have 1/4. And now, of course, here we have, here, notice we have 4 times pi over 12, which is pi over 3. So when we substitute here, we get this. So we have sine of pi over 3. Okay, so that's an easy calculation. I just did it here. So when you substitute pi over 12 for 4 pi, you get the pi over 3. And then minus, now we substitute 0, but that's going to zero everything out. So now, of course, you get 0 minus 0. And here we can just factor the 12. So let me put a plus here. So we'll have 2 over 12. And that'll just be a 5 minus a 1, which is a 4. So this gives us 8 So we have pi over 12. And here we have minus a 1/4. Of course, and sine of pi over 3 is root 3 over 2. And of course, here we've just got what plus what? That's a 6, right? 4 over 6. Now, these things will start to reduce, and this is where you think, well, do you reduce things and then go forwards to go backwards? Let me look at it this way. If I leave the 12 there and then an 8, and of course I've got my pi here. Sorry, I left the pi out. Let me just do it this way. There's a 12 there, so yeah, that'll make any sense. Do extra work and see if that'll make it easier. So let's just write that as an 8 pi over 12. So here we have, well, there we go, 8 pi over 12. So we've got one here and one here. So we've got 2 copies of that. So this will be times a 2. And here we've got an 8. So this will be minus a 2 times square root 3 over 2. So again, we multiply here, that gives us a negative 2. So now let's see, what do we have? So this, in this case, this will give us what? A 2/3 times a 2 minus a root 3. So this gives us a 4 pi over 3 minus root 3. And that's okay. I mean, we could factor it. I don't see why we couldn't. Would that, what, take out a 3 or 1/3? So if we do that, this will be a 1/4 of the area. So total common area would be 4 times this. So we get 4/3, 4 pi minus 3 root 3. So the thing about this particular calculation is that this is not a hard calculation. I like to do things so that they come out nice. And I don't, sometimes, ladies and gentlemen, you have to think about the algebra you're doing. You don't want to go forwards to go backwards. You got an 8 over 12 here, and why have to go back and get another common denominator? And then they turn out to be the same term. So boom, there you go. And so now we see that 1/3 of the quantity 4 pi minus 3 root 3 is actually this area, the red plus the blue. And then we have the symmetry here. So to get the area, the total enclosed area or common area, we hit that with a 4. And so there's our final answer. So I think this is an interesting problem. And so it kind of gives you a recipe for how you actually look at polar areas. Okay. And so when you're doing a polar area, look at the Cartesian to get a decent picture of the polar graph. So at least you have some visual that you can work with. And then if you've got an intersection curve, then compute it. Now, of course, if you're doing something where you've got some angles that aren't nice, like for instance, I've looked through an example where one of the angles was, this is what I used before, the arc sine or inverse sine of 2/3. I'm like, fine, just write it that way. And if you've got compositions, do your little triangle and rewrite things like we've done before. That can happen. But what I thought was important with this particular problem is that if you have 2 curves, the analysis part is very straightforward unless you're at the pole, where you could probably have the curves getting to the pole with different values of theta. So just keep that in mind. It doesn't normally cause an issue, but if you're just finding points of intersection, that could be, well, my equations don't show me that. Well, they're not going to show you that, because this is only going to give you common values of theta, which is, what we're accustomed to. So I like this problem because it kind of covers all the bases, the algebra, the analytic geometry, the pre-cal, all of that in one problem. Okay, now what I want to do is take this discussion to finish up the arc length here. So in order to do arc length, we just have to make a few adjustments. Arc length with polar curves. We know what it is. We've got the parameterization. We do x prime squared plus y prime squared square root. So for polar, remember, we have r is r theta. Okay, and this is, and again, this is a nice curve. It has to be C1. You know, we know that when we're doing arc length, and so we know what x, the polar coordinate transformation. We have r cosine theta, and y is r sine theta. You'll use this in Cal 3 until you're sick of it, but it will be your bread and butter. Polar coordinates are, like I say, very important. And you know, the computations you do with them are not always trivial, as we just have seen with the problems we've done today. So now we want to get the x squared prime, or excuse me, the x prime squared and the y prime squared formulation, so we can have a nice formula to work with. So now what we see is x prime is r prime cosine theta. We've done this before. This is old hat when we're doing the vertical tangents and all that. So this is stuff you've seen before, minus r sine theta, the derivative of cosine being the negative sign, and y prime is r prime sine theta plus r cosine theta. And then we just want to look at the square. So this is not hard, but you need to see where it comes from. So you don't have to memorize this. You could put it on a note card, but now from the parametric representation of arc length, we need to do this construction. So we simply square both of these and add them up. So this will be r prime cosine theta minus r sine theta, quantity squared, plus r prime sine theta plus r cosine theta, quantity squared. So we can expand these. This is not hard. So this is r prime squared cosine squared, like we're doing spherical coordinates, minus 2 r prime r cosine theta sine theta plus r squared sine squared. Now we'll move to this one, plus r prime squared sine squared plus 2 r prime r cosine theta sine theta, the middle term, so to speak, and then plus r squared cosine squared theta. So the algebra, the trig will make us happy with this. Of course, these absorb, right? These absorb. And then we can put these two together with the fundamental identity and these two together. So this will give us what r squared times cosine squared plus sine squared plus r prime squared cosine squared plus sine squared. So now when you look at this, these are both 1. So we get r squared plus r prime squared. So that gives us the radicand. So now this implies that arc length will just be, of course, if we do alpha to beta. So we have the square root of what? Well, I don't have to put parentheses with that. You can put in the theta dependence if you want, r squared plus r prime squared 1/2 d theta. So that's what we were looking for. So now we have a formula for the arc length that not only work, we know we have one that works for parametric representations in general, but since polar coordinates are so important, we now have our standard formula for that. So you don't do this every time, clearly. You could, but this will stick. And so this becomes a nice formula to put in the back pocket. And now, of course, if we think about we can extend now we can extend area formulas for the surface of revolution. It's amazing. This new IPEVO is the best. It just so clean and smooth. When I lecture, I'm so glad. I need to send them an email saying thank you for upgrading the software. It really is nice. They certainly got their computer engineers at work. So now, of course, number one, we'll just say revolve about, and we're saying in this case the curve. Let me just write that in. No need to leave it out. Revolve curve about polar axis. So this will give us S will be 2 pi alpha to beta. And then, of course, the distance to the polar axis will just be r sine theta. And then we'll have our square root bit. We don't have to start from scratch. We just use what we worked out in chapter 7 with the frustum. Do it once, no, not 3 and 4 times. Not efficient, right? And then revolve curve about theta equal pi over 2. The y-axis, so to speak, or theta equal 3 pi over 2, your choice, or theta equal 5 pi over 2. Of course, we infinitely many, right? S, so we have 2 pi alpha beta, distance to the theta equal pi over 2 axis, r cosine theta, r squared plus r prime squared 1/2 d theta. So this just gives you the formulations that you need for polar. Okay, so let's look to see how we can use them. Very simple derivation, but important. Now, there's a nice example that I want to go through that to do a arc length of a polar curve, and this is another cardioid. I'm not the cardioids just give you such nice examples. So we have r equals 1 plus sine theta, and we want to compute length of curve. Now, we can use symmetry here because we know we have some issues with this curve, and we want to keep life simple. So we can't mow over cusps and things like that, which we know the cardioid's going to have because A and B in ratio is 1 here. So first, let's just get a picture and decide how we're going to set up the integrals. And I'm going to show you a little trick with the integration, which when do we not need to have algebraic tricks for integrals? Okay, so here we just have 1 plus sine theta. So this is going to give us a nice heart-shaped curve. So we have 0, 1, and 2. So much pre-cal in calculus. I mean, why do you call it pre-calculus? I don't know. We should call it college algebra and trigonometry. I don't know, pre-cal, whatever. I think people say pre-cal and they don't understand. It's like when you play the game Monopoly. people don't understand this is about big business, monopolies. You know, people think, you know, we have so many phrases we use in English in even in other languages, then we just know them by hearing them, but we don't think what they mean. And so when we say pre-cal, we might say, well, it's just a class. Well, no, it's a class to prepare you for calculus. Sometimes I have to tell my students, do you understand the definition of the title of this class? I said, it's important. It's just so funny how we operate. We really struggle at times. So here we've got what? Pi over 2, pi, 3 pi over 2, 2 pi. So we've been cutting things down by halves. Sometimes we do by thirds when we did that rose curve with the cosine. It just depends. So now, of course, we have a 0, but we're booted up by 1. So this is just a vertical shift upward by 1. So here we see we've got a really interesting situation with the radii. We don't have any negative values, but we're going to have an issue right there. So the thing is that when we draw this, we're going to see some symmetry. We're going to get the heart-shaped curve, but let's just see. There's not going to be a loop. That be sure to look at the ones with the loop. Those make good calculations for areas. That had the you know, like I say, the inverse sine of 2/3. I thought that was an interesting example. So now when we start out at 1, so we can mark off like a 1 and then a 2 and then a 1. This one's like cookie cutter, and then back to here, obviously. So now when you start out, you're at 1 and you increase when we get to pi over 2 up to 2, but not where we're bowing out like we did with the last one. Because we increase there, we don't drop into it. Same on this side. Same on this side. We've got some nice symmetry with respect to the polar axis there. Well, this pi over 2, not that's the polar, but this one. So you could check symmetry there. And then of course, as we move here from pi to 3 pi over 2, we end up at the pole. So we get something like this down, and then we get that heart shape. And then we move back around here like that. So the idea is that we move to 0 and then we move back out. That's where the cusp occurs. That's where the issue is, okay? So what I would suggest here, since this is fairly simple, is to integrate here from 0 to pi over 2. So we'll just call this 0 to pi over 2. And then integrate from pi to 3 pi over 2. Pi, 3 pi over 2. And just double this and double that, and you'll get the entire curve. That way you don't have to worry about messing up here. These are maybe a little bit easier values. So again, and we can double, double, and double. So that would be a game plan. This is kind of a standard problem you do in calculus too. And it's a very straightforward problem, but it opens the door to a technique in computing the integral that's easy. You've seen it before, but I want to remind you of it. So now what do we need? Well, we've got what? R is 1 plus sine theta, and R prime is just what? Cosine theta, the derivative of sine. So now R squared plus R prime squared. So we get 1 plus sine theta squared plus cosine theta squared. So this will give us 1 plus 2 sine theta plus sine squared plus cosine squared. But now, of course, cosine squared plus sine squared is 1. 1 plus 1 is 2. So this gives us 2 plus 2 sine theta, which we can write as 2 times 1 plus sine theta. Okay, so the thing about this problem is that this is giving us algebra we expect, but the analysis here is not as hard as the one for the area. Obviously, we much simpler here. This is a simpler curve. So now what we can do, and again, never underestimate the Cartesian. It will always open the door. Just be careful when you do this work. I'm very meticulous about the work because every part is important. Even working with the algebra, with the computations, even though it seems overdone, it's better to overdo than to underdo, because if you overdo, you can always work back through your work and find any issues or any clarifications that you need. No work is no evidence. Okay, so now we're like, all right, so this implies that we have ds, and we're going to operate on this first, will be the square root of 2 times the square root of 1 plus sine theta. And you're thinking, he's crazy. Why is he writing those radicals? He always does 1/2. I don't know. We'll just do it this way. So now what we can see is we're going to do the conjugate method here because this is untoward when we want to integrate. So we'll have square root 2. So I'll just do this 1 plus sine theta 1/2 times 1 minus sine theta, because we're lazy. We like the conjugate method. We don't have to bring out the difficult techniques here. Excuse me. So this will give us the 1 minus sine squared under the radical. So we have square root 2, 1 minus sine squared. So this is old hat. This is Cal 1, but still good stuff. Now, of course, this is just, excuse me, cosine squared theta. So now we have the square root of cosine squared, which is absolute value. So this gives us square root 2, bring this upstairs, 1 minus sine theta, add 1, divide by the new power, my favorite technique, absolute value of cosine. Sometimes it's better just to do this first. I know you all like to write your integral signs 500 times, and that's fine, but I do that on the arithmetic part. But it's fine. We all have our techniques. It just again makes me feel good to see that you all are bringing up your level of computation. We don't always think that short is best, least is best. Work through it, and you know what to do. Now notice here, this we can now see that it's actually improper at pi over 2, but we can repair it. You could just mow over this and it'll still work. We can repair it. And here, no issue whatsoever. So now we can look at this and say, u is 1 minus sine theta, du is just, now this will be the derivative of sine is cosine. So we've got the negative cosine theta d theta. And we can use whatever the region is to figure out what the absolute value of cosine is. And here's our substitution, which we can think of as we write to make it table ready. So now let's do it. So this implies S equals, now for here, notice we've got 0 to pi over 2 where the cosine is positive. So we're going to need to throw in a negative and pay for it. So this is going to be, will be 2 with the negative. We need the negative because, again, we're going to have to throw in the negative here because the absolute value of cosine for this region is positive. All right, just positive cosine. So we get this, and we get what? The integral 0 to pi over 2. We have square root 2, 1 minus sine theta to the negative 1/2 negative cosine theta d theta. So we had to stick that in here. We didn't have it. We did not have the negative here because that's positive cosine for this region. So we got to pay for it out here. Okay, so that's good to go. And then this will be a improper integral, but we can easily fix that. And then we have what? Plus 2 times this integral. But now notice in the third quadrant, the cosine is negative, so the negative is built into the absolute value, so it's already there. So now we've got what? Square root 2, 1 minus sine theta to the 1/2 or negative 1/2 negative cosine theta d theta, already there. So again, what's interesting about this is that the absolute value didn't help us here, so we had to pay for the negative. The absolute value here hooked us up. So we had that. So just remember that we have to respect the arithmetic of the trig functions. And so now when you look at this, you can see that when we, this is why you don't necessarily have to write this as improper. Notice when you do the antiderivative, you bring the 1 minus sine theta upstairs. So that erases the issue of the fact that this is infinite at pi over 2, because that's 1 minus 1. So that's 0 in the denominator. So basically, this is b approaching pi over 2 from the left. But you can see when we integrate, that'll be okay. So basically, this is improper, but it's fixable. To say improper, we'll say infinite at pi over 2. But we can fix it. When you integrate, you get rid of it and you can pass to the limit, which you'll see. So I'm not just saying forgetting about this. I'm showing you that, and then as we integrate, we will be able to evaluate the integral. So just to save a little time, but that's exactly what's going on. So here we have what? Negative 2 root 2. Add 1, divide by the new power. So the new power is 1/2. So times 2. 1 minus sine theta to the 1/2, now repaired, 0 to pi over 2. So happy face. We're happy about that. Looks like Professor Ron's, same hairline. So now when we look at this over here, same thing, but this is proper. So this is going to be what? Plus, table ready, 2 root 2, 1 minus, oh, and of course, add 1, divide by the new power. Let me put that in. No need to leave that out. Times 2, 1 divided by 1/2, 1 minus sine theta to the positive 1/2. Now we've got what? Pi to 3 pi over 2. So now we've got what? A negative 4 times a root 2. Now we can substitute pi over 2. So of course this will be a 1 minus a 1 to the 1/2 minus, now we substitute 0. That'll be 1 minus 0 to the 1/2. Okay, plus, this is a really nifty problem. I like this problem. 4 root 2. And now we have what? Substitute 3 pi over 2. So again, the 3 pi over 2 is going to be negative, right? So that's going to be a negative negative. So this will be 1 plus a 1. And then when we look here, we've got 1 minus sine of theta. That's 0. So we have minus 1 minus 0 to the 1/2. So now what do we have? We've got negative 4 root 2. And here we've got negative square root of 1. So that's times a negative 1. So again, notice here, negative square root of 1, negative 1, plus 4 root 2 times the 2. Oh, 1/2, sorry. That's a 1/2. Don't forget the 1/2 right there. That does make a big difference. And then here we've got 4 root 2 times the -1. So now, of course, these absorb because this will be a plus, negative times the negative. These absorb. So absorb. And then, of course, here we've got root 2 times root 2, which is 2. So we get 4 times 2 squared, which is what? Oh, ding, 2. Let me just write this out the way it is. This is just going to be root 2 times itself. And that's 4 times 2, which is 8. Now notice this is really important about this part here, because see, without configuring this correctly, you can really run into some arithmetic problems. And of course, you have to remember the 1/2. So the key here is to write when you've got an integrand that requires some surgery, do that first and then look to the calculation. And then we can see by the proper analysis here of the absolute value, these two terms actually absorb. And that's kind of interesting. And then notice here, we get the 1/2, so we get the root 2 times the root 2, which is actually 2. And we get 4 times 2, which is 8, which is another crazy answer response for a polar calculation. We got 6 for the lemniscate interior area. And here we're getting an 8. It's crazy. It's like so refreshing compared to what we used to get with the other problems. So that's really nifty. Now, there's one example I want to mention before we close. And it's an example I usually do, just to give you a quick example of an arc surface area. And there are tons of problems to do. I think about new problems to work in, but there's certain standard problems that every Calculus 2 student needs to see. And you know I love the torus. And so in this case, we want to compute area of torus. This is very straightforward. Area of torus. And what we do is we revolve circle R equal A about the line R equal B secant theta. So this is in terms of polar. So we're going to attack it with our new formula. In this case, where A, they're both positive, but A is less than B. Now this is the line right here. You can easily analyze this using polar coordinates. This is just the line X equal B, it's vertical. So just substitute, you know, X is R cosine theta, and you can easily show that X equals B. That's something you should be able to do without my help. So now when you do this, we've got this circle that we're revolving about this line. So let's draw a picture of it. So we got the polar deal. You're thinking polar with what looks to be Cartesian setup. So we've got what? R equals A. So we'll just mark this off. But we're changing this up where the axis of revolution is moved. It's not the polar axis. It's not the theta over 2 or pi over 2. So we've got this line here in our polar. So this is why this is done this way. We've got this polar curve here. This is the polar plane. And we've got this polar curve, which is really X equal B. So this is like, think Cartesian, so we can draw it. So we'll just write it out here. This is a beautiful problem. So I'm not going to write that. I'm just going to say R equals B secant theta. You're like, you're going to throw rocks at me. Well, we know it's that. We know it's that. We know it's going to look like this. And this is what R equals A. Okay, so we want to do this. And if we revolve this way, ladies and gentlemen, we do generate a torus. So now, when you look at this, you're thinking, well, you could just let theta run from 0 to 2 pi, because that's a nice curve, no issues with it. Or you could just go 0 to pi and double the result. But now notice if we take a theta here, we have an area of arc length. We need this distance right here. That's the distance to the axis of revolution. Well, that's easy to do because we just have Pythagorean. This is A. And this, of course, is just A cosine theta. So the distance we need is just what, in this case, the value B minus A cosine theta. So we're thinking of the distance from here to here. So when we look at that, again, this is the distance right here that we've defined, and we have to define this as we define the distance here. So that's a kink in the problem. So this distance will be B minus A cosine theta. And that's important. So again, we define this distance here. We know this distance here is just B. And normally we would just be thinking in terms of this, like we were going to the y-axis like we had before, but we have to amend it because we have the displacement here of the axis of revolution. Instead of being here, it's all the way over here. Okay, so that's the one kink in the problem that requires a little bit of work, but it's doable. All right, so now this implies, and I'll just double this result. I'll just take theta. I don't want you to get used to saying 0 to 2 pi, because when you start doing that, you'll mow over problems. And so I'm trying to keep you from doing that. So I'm going to let theta be 0 to pi, and we're going to double the result. So this is going to say S is equal to 2 pi. Now we'll have 0 to pi. And now what's interesting here is that we have R equals what? A. So R prime is 0. Well, hallelujah. So R squared plus R prime squared is A squared, right? So we like that. So now when we take the square root, we just get A. So this implies square root A squared is absolute value of A, which by definition is A. So now here we get the distance to the axis of revolution, which is B minus A cosine theta. And the element of the arc length will just be A d theta. So very simple. So this gives us 4 pi, 0 to pi. We multiply this out. This is AB minus A squared cosine theta, d theta. So now we can integrate. So this will be AB theta. And now, of course, the antiderivative of cosine is the positive sign. We've done that a million times today. So we have A squared sine theta from 0 to pi. Now, when you look at this, and I think what's interesting about this particular example that you see in this particular case is that all this analysis revolves on the techniques we've already been doing, just adjusted for polar coordinates. And so now when we substitute, we get 4 pi. Oh, say it, but don't write it, right? 4 pi. And this will be AB pi minus, and then of course this will be A squared sine of pi. That's clearly 0. And then, of course, if we put in 0, both of them 0 out. That's 0 minus 0. So this gives us 4 pi times AB pi. Of course, that's minus 0 too. So this gives us what we get 2 copies of pi. So we get 4 pi squared AB, which is a familiar looking formula. So the idea here is that when you think about what we've done throughout the course, we've really been jumping back to chapter 7. We found all these interesting formulas about integrals, you know, that gave us volumes, that gave us areas, that gave us, you know, of surfaces, that gave us areas of regions, that gave us lengths of curves. And you're going to continue to do the same thing when you get to calculus 3. It'll be the same thing. These will all, you'll get a more generalized version in calculus 3, which you can reduce to calculus 2. So what did I tell you that you always do in math? You just keep doing the same problems over and over. You just elevate the problems. You make them better because you add more mathematics. You make them more abstract, or you add more support so that the problems are actually more far-reaching. So what we're seeing here, and this is only the beginning of the polar coordinates. I've given you plenty, but the thing is that you will use this material over and over. This will be something that you will use all the time in engineering, more math courses, in physics. I mean, polar coordinates are your bread and butter. And I say that about pretty much everything, but the trigonometry, how it attaches to the polar coordinate transformation. You're going to see that in cylindrical coordinates. You're also going to see that in spherical coordinates, which are extremely powerful. And when you do double and triple integrals, you'll do polar integrals, double integrals, you'll do triple integrals in spherical and cylindrical coordinates, and then you'll do the vector calculus theorems, which used to be just the domain of advanced calculus. Now they've moved the vector calculus theorems into calculus 3, which I think is interesting. Even when I was in school, we did the vector calculus theorems. So the thing is that you will continue to use these concepts in former and following math classes if you choose to take them, that is classes outside of your curriculum. But as talking with many of the former San Jac students who are now engineers, they said depending on the discipline that you decide, if you're going into engineering or computer science, there's always classes that focus more on the mathematics, and you feel like you're taking a math class. So again, enjoy this for what it is. I think you'll see that the parallels are useful. There are several examples that one that I actually thought was very interesting that I kept talking about. This was one that I kind of made up myself. And it's similar to one in the textbook. I want you to work through, and I'll say about it. It's finding the inner loop area of this limacon. And it actually turns out to be very interesting, but that's what I was talking about, the inverse sine of 2/3. And so you get a nice computation with this. So it's not that these are overly difficult. They just keep you moving. They keep you challenged in using all of the mathematics that came before. That's what students don't understand. When I say I expect you to understand the prerequisites, I mean exactly that, because you have to use these prerequisites in such a way that you understand them. It can't be a cursory understanding. It's amazing how students don't believe that trigonometry is an essential part of calculus, that conic sections, sequences, algebraic maneuvering, solving equations, equation theory from college algebra, it's all essential in calculus. And so that's why I keep hearkening back to it. And the calculations are done by hand so that you can see them. This will make you ever ready to move into any challenge that you do. And of course, you computer science geeks, you're going to be coding. You're going to be coding all the time, and you're going to be making new algorithms to solve interesting problems. That's will all be mathematically based, and you'll enjoy that. Okay, so I'll have one office hour today, and then of course I'll have some tomorrow that I'll announce. Be sure to get your uh, signature assignment done. And then, of course, we'll do some review next week, and I'll have the announcement up for the final exam. So I hope you've enjoyed our little excursion into the polar coordinates and parametric equations. Maybe it's been a nice change from the series and the the power series and things, but it's all good stuff, and you will use it, and use it. So everybody have a great day. I'll see you soon. Take care.